We are going to look at a polyprotic acid, and this is page 11 and 12 of your chapter 14 homework packet. And a polyprotic acid is an acid that has more than one proton or more than one H plus to donate. So H3PO4 can actually get rid of all three H pluses. It does progressively get more difficult to get rid of each H plus, but we'll take a look at this. So we're supposed to find the pH of this solution and then some concentrations of H3PO4 after it loses one proton, after it loses two, after it loses all three. There are some different K values. So Ka1 is for getting rid of the first hydrogen, Ka2 is getting rid of the second one, and Ka3 is for getting rid of the third hydrogen. Notice how it progressively gets smaller and smaller and gets more difficult or favors the products less and less as you move in that direction. All right, let's take a look at H3PO4 breaks up into H plus and H2PO4 minus, and we're assuming you have 1 molar of this phosphoric acid. And it is a weak acid, so we assume it's not going to break down very much. And so X will be across here, and then this is 1.0 minus X. So typically, if X is really small, we can just call this 1.0. We're kind of on a borderline where maybe this is something that we can't make that assumption. We'll see that in a second. But let's take a look. Ka1 equals the H plus times H2PO4 minus over H3PO4. And you can solve and say Ka times H3PO4 equals X squared, or X equals the square root of the acid, or the Ka times the concentration of the acid, like we've talked about with monoprotic acids. So I take that, I plug that in, I get 0.07, and I kind of check and say, hey, this is a violation of the 5% rule. So I'm going to go and actually not do the algebra with the 1.0 minus X. Chances are you will not have to do that on an AP test, but we'll just take a look at how that's done. And let's see, here we go. We have a quadratic formula. And notice I got my X squared. This is my H plus and HPO4 minus 2. But then my acid, the H3PO4 is 1.0 minus X. So I'm going to plug it in that way. There's my Ka value. And I get all of this. And you can follow through and solve that. And ultimately, you get two solutions. One's a negative answer, which can't have a negative concentration, and the other one is 0.083. Let's see how that compared originally, and it's pretty close. This is a violation of the 5% rule, but not a drastic violation. So I would have, with the assumption I would have used 0.087, technically it comes out to 0.083 for the H plus, giving me a pH of 1.08. Just to give you an idea, if I would have used the 0.087, my pH would have been 1.06. So again, not throwing things off very much. It asks for the H3PO4 concentration. Without the assumption, we would just say it's 1.0, but in this case, we're going to say it's 0.92. So again, some effect there, not huge, but noticeable. Now, the next one is Ka2, and we're going to talk about H2PO4 minus breaking to H plus and HPO4 minus 2. So these progressively get less likely to break down because you have a bunch of charges here, and if there's charges here, it's going to be less likely to form them. Okay, so due to repulsion from those charges. Okay, so I'm going to keep going here, and I'm going to call this 0.083 because that's what we figured out. And we said H plus was 0.083 because that's what we saw for last time. And then this is 0. So we're kind of doing the second breakdown. And again, this is going to further break down, but we're going to assume that that X is really small to the 0.083. So we're going to still call H2PO4 minus 0.083. I don't know. I think that was one of the answers you're supposed to do. So that would be this one. Now notice the H plus, X is going to be real small compared to 0.083. So the contribution by the second one is not really going to be significant. And that's pretty typical if your K values are pretty far apart like these ones are right there. Okay, well, if that's the case, I can plug in H plus and HPO4 minus 2. And I can plug in this value. The H plus and the H2PO4 minus are essentially one's a minus X, one's a plus X, but since X is real small, they cancel each other out. And if they cancel each other out, then the HPO4 minus 2 is just the Ka2. So that's typically, if you have a diprotic acid, for example, the second concentration will be the same as Ka2, except you put a molarity on that. So that's really a shortcut to finding that piece. Okay, if I had to find the third one, which is pretty unlikely that you have to do that, is I would look and say HPO4 minus 2 breaks into H plus and PO4 minus 3. Again, because of all the charges built up, it's going to be even less likely to occur. And I can write the things down. This was the what HPO4 minus 2 was from the last part. My H plus is really big. I'm guessing this is going to probably be pretty small. And it ends up being pretty small. And ultimately, notice our assumptions, X can be insignificant compared to these. We plug things in, especially when you plug in that quite small Ka value, and we get 3.6 times 10 to the negative 19. So that one's going to be by far the least. And this one, the second one, where Ka equals K2, then we can scroll up. I'm sorry, Ka2 equals concentration of what after losing 2 hydrogens. And then we scroll up and we can look back and say, oh yeah, this was the constant, the 0.083 was the concentration of this, and the H plus probably the most important piece. So what's probably the most common question you're going to be asked with this is probably finding the pH. And to find the pH of a polyprotic weak acid, it's essentially all going to come from getting rid of the first hydrogen. So it really becomes like a weak acid problem. You can say the square root of Ka times concentration of that. This one, because we violated the 5% slate rule a little bit, then we had to do a little recalibration with that. But that's generally how you're going to do a weak acid problem of a polyprotic. It's going to be very dependent, H plus can be very dependent on that first association. That's where the vast majority of it will come from. That's what you have to keep track of. Okay, hope this helps with polyprotics. Thank you.